Yeah, we can start.
Where do we start? You start when I'm also there.
Welcome, my dear candidates. You're welcome to this lesson, our physics lesson. Once again, I'm your teacher, Ojambo, Geoffrey Joe, and this is my contact, and I'm going to take you through physics. And if you remember, from where we left it, my dear learners, we ended our lesson having discussed the relationship between capacitors in series, capacitors in parallel. As a quick reminder, let us look at the expressions. We said when they are in series, effective capacitance is going to be given by C1, C2 over C1 plus C2. This is, for only two of them. Is that it so? When the two capacitors are in series, that is what it's going to be. When they are more than two, suppose they are three, it will be 1 over C equal to 1 over C1 plus 1 over C2 plus 1 over C3. And then when they are in parallel, we discovered that it will be C equal to C1 plus C2 plus C3. That is the quick reminder. However, if you remember very well, my dear candidates, we said we would start off by looking at some worked examples. It is at this moment in time that I want us to have those examples. Worked examples. Worked examples. We can look at one or two, then we shall be able to have our next objective. Suppose a question is set and it says, 1, a network of capacitors, of capacitances, capacitances 40 microfarads, 50 microfarads, and 70 microfarads is connected to a battery of 9 volts. 9 volts. Suppose this is the diagram. Something like that. This is the battery which has 9 volts, or the source of EMF, 40 microfarads is here, 50 microfarads, and then 70 microfarads. And the question here is, calculate the charge stored. Calculate the charge stored. Charge stored on the 50 microfarad capacitor. On the 50 microfarad capacitor. That's the first example we have. So the question wants the charge stored on the 50 microfarad capacitor. 50 microfarad capacitor is here. Now, when you look at our setup, this is our battery. This is our source of EMF. Charge moves. You see? Now, when you look at this here, suppose I covered off this. Suppose we covered off this. What do you discover? You discover that the 50 microfarad capacitor and 70 microfarad capacitor are connected across each other, which means they are in parallel. Isn't it so? So we can start from there and try to find the effective capacitance there. And we say, so in our solution, we shall say capacitance across parallel connection. C will be equal to, since they are in parallel, what did we say? When they are in parallel, total capacitance is equal to the sum of each of the capacitances. So it will be 50 plus 70, which will give us 120 microfarads. Now, if I'm to just draw something very simple, you'll discover that our circuit now reduces to something like this. This is 120 microfarads. This is 40 microfarads. This is 9 volts. So how does this help? This helps us to be able to get the total charge from which we would be able to go ahead and find. Now, because they are in series, PD across this one is different from the PD across this one. But since the 120 represents the parallel connection between these two, therefore means the PD across the 50 will be equal to the PD across the 70 microfarad capacitor. So our task is to find the PD across the parallel connection from which we can be able to get the charge because we have the capacitance. From here, total capacitance, C would be equal to, since now we are remaining with just two of them which are in series, effective will be given by 120 times 40 over 40 plus 120. If you remember very well, when they are two in series, the effective is given by product over sum. And this is now going to be, when you get your calculator, 12 times 4 is 48, 1, 2 zeros, over 160. I think that is correct mathematics, isn't it so? Good. So C therefore becomes, is it 30 microfarads? We can cross-check, by the way. We can cross-check very quickly from our calculator. 120 times 40 divided by 160. It gives us 30. So having got the total capacitance as this, we have the total PD. We can now get the total charge. Okay? Total charge, Q is equal to CV. When you substitute, you'll have total capacitance is 30 times PD is 9, which gives us 270 microcoulombs. Since it's not the final answer, I can still work in microcoulombs. I can leave it there. 9 times 3 is 27, isn't it so? Then times the 0, times the 10, 27 times 10 will be the 270. Now, this is the total charge, which is here and here. So we can now go ahead and find the PD across the parallel connection. Okay? PD across parallel connection, PD across parallel connection or parallel network, V will be equal to, I can call it V1 to show a difference, it will be Q over C. The charge, since these two are in series, charge is the same, we have already discovered. So it is therefore going to be equal to 270 microcoulombs divided by, I can choose to keep the unit silent, divided by capacitance is also 30. Am I right? Not 30. We are looking at the one for the parallel. This is now where one can make a mistake. They can bring in 30. When you bring in 30, you are gone. But we want parallel, and the parallel connection is represented by the 120. Together, so divided by 120 micro what? Farads. So the units will cancel, and then the units of micro will cancel. So we shall remain with, this is going to give us 120 is going to give us 27 divided by 12. 2.25. I don't know what my friends have got, but I have got 2.25, and this is what? Volts. Now this PD is the PD across the 120, but the PD across the 120 is therefore the PD across the parallel network. Why do we say so? The 120 microfarad capacitor is a result of these two, the 50 and 70, which were originally in what? Parallel with each other, if you remember my candidates very well. So what does that mean? We can now be able to go and find the charge which is stored on the 50 microfarad capacitor. Why? We have the PD. Since these ones are in parallel, and we discovered that PD across parallel network is the same, it therefore means that the PD across the 50 microfarad capacitor is the same as the PD across the 70 microfarad capacitor, which is 2.25 volts. So charge on 50 microfarad capacitor, that is the charge stored, will be equal to, given by, is equal to Q, which is equal to CV. The capacitance in question is 50. So now, since we want the final result, we can have it given as 50 exponent negative 6. I have divided by 1 million. I'm changing it now to coulombs times the PD, which is 2.25. This is a decimal point. It may look like a 0. So when you multiply through, what do you come up with? Let us see. 50 exponent negative 6 times 2.25 gives us 1.125 exponent negative 4. This is coulombs because we're talking about charge. Okay? So, you can see that this question has tested so many things. What are they? It tests our knowledge about the parallel, about the series, and then eventually the relationship between charge, PD, and the capacitance. So this is our example 1. We can look at one other example, which can now take us to the next aspect. Okay, example 2. Example 2 says, of course, I'm writing down this question as people copy down this example. I presume that by the time I finish writing down question 2, we shall also have finished. Isn't it so? So example 2 says a capacitor X, of 5 microfarads and another Y of 8 microfarads are connected in series with a 20 volt supply. Full stop. Calculate the, can put a colon here, Roman 1, charge on X, Roman 2, potential drop, across X. That is what we have, my dear candidates. So here, you try to think when the question is given, try as much as possible to examine yourself and see, am I in relation with what the question is asking? If you don't make sense out of what you have read for the first time, read it again and see to it that you make sense out of it. Together? So here we are. They are talking about them being connected in series. So in our solution, suppose we look at the solution. I believe we have finished copying down the other one. We shall have these as the capacitors. from the interpretation, this is what we have. A capacitor X, suppose this is X, and it has 5 microfarads. It's of capacitance 5 microfarads. And another Y, and it has capacitance 8 microfarads. Are connected in a series. This is the series bit. With a 20-volt supply. Here we are, 20-volt supply. Do you see how we are diagonizing the question, my dear candidates? Then, after that, they have told us to find the charge on X, charge on X, charge on X. There we are. Now, before you find the charge on X, there are certain facts we need to remind ourselves of. What are those? What are those facts? One, we discovered earlier that in our previous lesson, if you remember, that when you have 2 capacitors which are in series, the charge on each of them is the same. Isn't it so? That is one fact. Then another fact we also discovered was that when you have 2 capacitors which are connected in series, their effective capacitance or their total capacitance is given by the ratio of their product to their sum. So we can start from there and get the charge. So we can say total capacitance, this is L, total capacitance C would be equal to Cx times Cy over Cx plus Cy, where the subscripts are representing the respective what? Capacitances. So we can now substitute and say, so the effective capacitance would be 5 times 8 divided by 5 plus 8. This is going to give us 40 out of 13 microfarads. I can keep it like this. It's not my final answer, but I can still go ahead. Now, the reason as to why I'm keeping it like this is to try to keep the degree of accuracy, okay? So that I don't over truncate or I don't over round off. Now, having got the total capacitance, we have the total PD. We can go ahead and find the total charge. So, total charge, Q is equal to CV, which is going to give us our total capacitance is 40 over 13 times our total PD is 20 volts. And so our charge is going to be equal to, when we press our calculator, at this point we can go ahead. It is going to be 40 divided by 13 times 20, which is going to be 800 over what? 13, but we can take it to the smallest factor. So 800 divided by 13 is going to give us, I'm getting an answer which is 61.54. Now these are microcoulombs, but you can change it to the SI units class, and that is going to become, you divide this by 1 exponent 6, to be, in mathematics, if we are to write it in scientific form or even in science, it will be, or in physics, coulombs. So that is what we are getting, okay? 6.14154 exponent negative what? Exponent negative 5 coulombs. Now, having got this, I can help myself. How? By saying I can conclude, so that I don't leave the person looking at my work in suspense, by saying, since capacitors X and Y are in series, okay, and we know that charge on capacitors which are in series is the same, therefore, so I can say, since capacitors in series have the same charge stored, then charge on what? Charge on X. Charge on X is equal to 6.154 exponent negative 5 coulombs. Hope we are together, class. Remember, we are getting it from here. And having got this as total charge, and these two are in series, we know that since they are in series, effective charge is going to be the same on each of the capacitors. So that is how we come up with this answer. Then Roman 2, the potential drop on X. Potential drop is the same as potential difference. So the Roman 2 shall say potential drop on X, we shall say V is equal to Q over C. Then it's so? That is what we're going to have. So this is therefore going to be equal to, our charge is 6.154 exponent negative 5 divided by the capacitance on X. What was our capacitance on X, class? We were told it is 5 micro. So it's 5 times 10 power negative 6. I am changing it from microfarads to farads. Therefore, the potential drop on X, V, will be, when we get our calculator, 6.2. It is 6.154 exponent negative 5 divided by 5. Then divide by 1 exponent negative 6. I have got a PD of 1.23 volts. Of course, it continues, it is 1.2308, but I can simply give it as what? As that, 1.23. So that is our answer, which, I beg your pardon, I think it is 12.3, not 1.3, isn't it so? It should be 12.3 when I calculate again, because it is 6.154 exponent negative 5 divided by 5 exponent negative 6. Yeah, it is 12.3. Okay, 12.308. I can give it to one decimal place, 12.3. Okay, so that is our second example. And I think these two examples can be able to take us through, or can be able to open our minds more about how we can be able to relate the capacitor arrangements. So in the two examples, we discover that our concepts must be on the fingertips. Why? Because as you work through, you do not know what they are going to ask you to give or to solve. So the most important thing here is knowing how to do what? How to play around with each of them. Having discussed that, I want us to look at the next aspect, and that is energy stored in a capacitor. Energy stored in a capacitor. Energy stored in a capacitor. Now, we have talked about charging, if you remember. It was one of the first aspects we discussed under capacitances. We talked about charging a capacitor. Now, when the capacitor is charged, we're able to discover that it stores, okay, that charge in form of electric potential energy. Now, how is this energy stored related to the capacitance or to the charge or to the PD, okay? If we assume that at an instant, you imagine, at an instant t, or at a certain time, the capacitor is charged, okay, to a PdV, and the charge on it is Q. We can say, suppose at an instant, or at any instant, a capacitor is charged to a PDV and stores charge Q. And stores charge what? Q. Now, if it has stored this charge Q class, in any attempt to increase the charge stored, what shall we do? We shall be able to have the PD done what? Increased. Now we can imagine, suppose a charge dq is to be transferred or is transferred, okay, from one plate of the capacitor to another, then the PD increases to V plus a small change in what? V. If we are transferring charge of dq from one plate of the capacitor to another, that means our PD will increase by this. So which means the PD now will have increased. Remember, initially it was charged to a PDV. Now we have more dq. I mean, yes, more dq transferred, implying that even the PD will increase by that. So the total PD now becomes V plus dV. And now we know that as the charge is transferred from one plate to another, there is work done. And it's so? So what is the work done in that case? Work done to transfer, okay, the dq will be given by, to transfer charge, let me say, to transfer the additional charge, will be equal to the small work done in charging that capacitor will then be given by, what do we know? It is our Q, okay? Am I right, class? It is our dq, which we are transferring, times V plus dV. Isn't it so? But now, remember what we said, that this is a small charge which we are transferring. Then that means even this PD is going to be a small what? Change in PD. Now, since it's a small change in PD, it will be so small compared to this. Therefore, this is going to be approximated to V, meaning that our PD will be presumed to remain constant. So I can put that in writing and say, since dV is small, okay, then V plus dV is approximately equal to V, i.e. the PDV is presumed to remain, or is assumed, I can just use the word assumed, is assumed to remain constant. So what is that? That means our small work done, or our change in work done, will therefore be equal to dq times V, which I can write as V dq. But what we know? But from our relationship, but from Q equal to CV, okay, our V is equal to Q over C, which means our expression dW will become, class, when we substitute, it will become Q over C dQ. Am I right? Now this is the small work done. Now you imagine instead of only transferring this small charge, you are doing work totally. Okay? You're charging it from a charge maybe 0 to a charge fully, that is if you have to charge it fully, to a charge Q. You will then have total work done. Okay? So which means total work done, W would be equal to, this now becomes a full D, which is going to be equal to integral of Q over C of dQ from charge equal to 0 to charge equal to capital what? Q. We know by doing this we are finding the total charge, we are summing up. Isn't it so? Now, from the integration, which we have studied my candidates now, by now, our W, our work done will therefore be equal to, this 1 over C is a constant, so we shall integrate Q with respect to Q. It will become Q squared. But we already have our 1 over C. Q squared over 2, but this 1 over C is there, so it becomes Q squared over what? C. That is now, and it is from the limit 0 to the limit what? Capital Q. Now, when we go ahead and substitute, what do we come up with? When we substitute, we shall have our expression becoming our work done will be equal to Q squared over 2C minus 0. Because when you put 0 here, everything will go to 0 or will come 0. So that means our work done is equal to Q squared over 2C. So this is the charge stored, my dear candidates. Okay? This is the charge what? Stored. And this charge stored, I beg your pardon, this is our energy stored. We are looking at energy stored. So our energy stored is given by Q squared over 2C. We can have this energy stored expressed in other expressions by bringing in this expression Q equal to CV. Suppose we substituted here. That work done, which is the energy stored, will also be equal to CV everything squared over 2C. From here, that means it's going to become CV squared over 2. That's another expression for the energy stored. Okay? Then also, from the other expression, we see work done is Q squared over 2C. From 1 over C equal to V over Q. When you substitute there, you'll have work done is equal to Q squared over 2 times V over Q. What does that become? It is going to become QV over 2. And this is another expression for the energy stored. Now, I want us to have something discovered. Having looked at all the 3 expressions, we have seen this, we have seen this, this, and we have seen this. I can put a W here. When you look at the charging process, as we charge a capacitor, it eventually is able to store charge. Isn't it so, my candidates? So after it has stored charge, that charge, as it moves from one capacitor plate to another, is going to be stored in form of electrical potential energy. Now, when you look at the energy supplied, I can call it WI, okay, by the battery, we see you have Q, the charge which is transferred, times the PD across the capacitor plates. Am I right? Yes. Now, finally, we discover that the work done, which is our final energy stored, is a half of that because it is QV over 2. Now, the question is, where has the other half gone when you look at the two? Because you would expect that since you're feeding in this, you would also get this QV. But you discover that we get QV over 2. This implies that as we charge okay, some energy is lost. And that energy is lost in the form of heat. Is lost in form of what? Heat in the connecting wires. Heat in the connecting wires. Remember, as we charge the capacitor, charge moves from one plate to another. And as it moves so that it can equalize the voltage or the PD across the capacitor plates to the PD across PD of the supply. And in so doing, I don't know if you have discovered, the wires become hot. So the heat there is as a result of the transfer of what? Charge. Therefore, you discover that our final expression is QV/2, implying that some of the potential energy which would be stored is lost. The electric potential energy is lost in the form of heat in the connecting wires as the voltages do what? Try to equalize. Hence, these wires normally feel what? Hot or warm. So this is how we can be able to get the expression for the energy done what? Energy stored in a capacitor. Of course, there are other expressions, my dear candidates. There are other expressions which, I beg your pardon, there are other methods which we can use to determine or to get the expression. But because I want us to also look at how we can calculate this energy stored, I want us to go to the next bit, okay? Which is the bit of trying to apply that formula. Remember, our lesson objective was to, first of all, we looked at those examples, if you remember very well, which had capacitor networks. And from there, we have been able to look at how we can be able to derive the expression for the energy stored in a capacitor. So we want to now employ or apply that formula. Example. Suppose we have an example. Example. We can say two capacitors. I can say examples, and I have one. The first one, two capacitors of capacitances 2 microfarads and 3 microfarads are connected as shown below to two batteries A and B, two batteries A and B, which have EMF 6 volts and 10 volts respectively. Then here this is the diagram. That is our circuit diagram. Make sure these ones touch, because it will look like there is no connection if they don't touch. So this is A, this is battery B, this is 3 microfarads, this is 2 microfarads. Let me write this clearly. It looks like a 3. 2 microfarads. So the question says, find the energy stored. Find the energy stored. Find the energy stored in each capacitor. In each capacitor. That's what we have, okay? Let us try to look at that. And see how far we can go. I believe as I erase the board, my dear students are writing down the question so that by the time I finish, we are together and we start working out. Okay. Suppose we start now. We are not supposing, but we are starting actually. This is the information. 2 capacitors of, and this time it is even very simple. They have given us the diagram. You can see the diagram and interpret. These 2 are in series, just like they have said. Okay? But they didn't tell us in the question that they are in series. But by looking at the circuit diagram, you are able to tell that they are in series. And so, students, then from there, what do we know? We know that A is a battery of EMF 6 volts. Can I put here 6 volts? Then B is a battery of EMF 10 volts. There we are. Now, what do we know? We know that when they are in series, charge is the same. You know so? But PD is different. We can use any of the available formulae. Remember, we have QV over 2, CV squared over 2, and Q squared over 2. So you can use any of them depending on what quantities you have. So suppose I start by getting the energy stored by a 2 microfarad capacitor. Energy stored by 2 microfarad capacitor. We know E is equal to, now because I have the capacitance and I have the PD, I can use the other formula, which is CV squared over what? Over 2. Is that it, so class? Then we substitute, we shall have E is equal to, what is our capacitance? It is 2 exponent negative 6 times, the PD is 6, so it will be 6 times 6 divided by 2. And when we do that, what do we come up with? Our E is equal to, here you can get a calculator. I know some of us can be able to work it out very quickly and we get an answer, but yeah, it doesn't harm. Okay, get your calculator, work it out very quickly. So it's going to be 2 exponent negative 6 times 6 times 6, that gives us that divided by 2, which is 3.6. Now, someone might ask, why does this man have to use a calculator? Yet this looks to be simple mathematics. My dear, don't take things for granted. It would be very disheartening to fail at this stage. We are talking about energy, and the SI unit for energy is what? Joules. So that is the energy stored by the 2 microfarad capacitor. Let us now look at the energy stored by the 3 microfarad capacitor. Energy stored by 3 microfarad capacitor. Something to note, you discover that whereas the PD across the 2 microfarad capacitor was given, this one was not given. However, from the facts we know that the total PD, which is the 10 volts, is got by adding the PD across this and this, since they are in series. So we can get the PD across 3 microfarad capacitor. PD across 3 microfarad capacitor will then equal to 10 minus 6, which is 4 volts. Then it's so? Now we have the voltage, my dear learners. We also have the capacitance. We can still use the same formula. So we can say E is equal to CV squared over 2. When you substitute in the formula, allow me put this here. It is going to be 3 exponent negative 6. I have changed it to farads. Times, the PD is 4, so it will be 4 times 4 divided by 2. Am I right, class? Yes, that's the correct substitution. And then when you work through, what do we get? Of course, this will be divided here. So we shall get 2, and I think the answer would be 2.4, but let us prove and see. 3 exponent negative 6, 3 exponent negative 6 times 4 times 4, that gives us 4.8, divided by 2, yes, 2.4 exponent negative 5. So our energy stored in this case is 2.4 exponent negative 5 joules. Okay, class? I think we have been able to successfully work out the energy stored by each capacitor. Now, you see that in this case, the question wanted the energy stored by each capacitor. But in some cases, they can ask you to get the energy stored in only one. Isn't it so? In only one capacitor. Suppose we find such a question. And that is going to be our second example. Let us look at this one here. Let us look at this one here. But this one I'm going to leave you to work out first. I want you to work it out first so that you can be able to discuss it when we meet again. In the diagram, below, C1, C2, and C3 are capacitors of capacitances, 40 microfarads, 30 microfarads, and 20 microfarads respectively. Okay? Then, with air as a dielectric, so this is the diagram, my dear learners. This is 90 volts DC. This is C3. This is C2. This is C1. You see? That is the diagram. Now the questions are, Roman 1, they say calculate the energy stored in the circuit, when all the capacitors are fully charged. Roman 2, they say the change in energy stored in the capacitors if the space between the plates of C2 is now filled with an insulator of dielectric constant (3). There we are. You see, class? that is our second example. This is the diagram. And they are asking us to calculate, it's almost similar to the first one. Eh? They want the energy stored in the entire system. And then after that, they want us to look at the energy change, okay? When you insert a dielectric constant, a dielectric of the electric constant 3 between the plates of C2. Now, remember we said we would be able to look at it. Then in our next session, when we meet again, we would be able to do what? To have it discussed further. But the clue we can take on here, class, when you look at this, we can try to look at it sheepishly as we wind up our lesson. When you look at these 3 capacitors, here we have a DC source. But then, you imagine this DC source were not there. Suppose I covered this here. What do you observe? You discover that C1 and C3 are capacitors which are in parallel. So you can start from there. Get the effective capacitance of C1 and C3, which are in what? Parallel. Now, the effective of those two will give us a connection where the capacitance C1, C3 is in series with C2. Then work through and get the total charge, from which you can be able to get the total energy stored. Because you now have the PD, you have the charge. Okay? Then you come to the second one and see how to go about it, having inserted here. Of course, there will be change in capacitance. Now, I want us to have our lesson end here, class. And don't forget to follow the Ministry of Health guidelines. When you must move out of home, put on a mask. Wash your hands for at least 20 seconds, as we are told. And we once again want to thank the Ministry of Education, together with UBC, for this service. Thank you very much. Stay tuned to your #1 broadcaster. Have a blessed day.